Let us start this lecture a thought process from Swami Vivekananda, who says, I would call him as a traitor who, having educated at the expense of the society, not paying least heed to the society. So, what we will do now, we will try to recapture or recall what we learnt in the last lecture. If you look at last few lectures, we are basically focusing our attention on the first law of thermodynamics, and we have derived that first law of thermodynamics for what you call control mass system, right, or a non-cyclic process. For a non-cyclic process, we have derived the relationship from the actual first law of thermodynamics, which is cycle integral of the work is proportional to cycle integral of the heat interaction during a process. So, if you look at like we have taken several examples, of course, for a simpler systems, like where some of the variables will be remaining constant. For example, isochoric process, isobaric process, isothermal process, adiabatic process, right. For all these processes, we have learned how to apply the first law of thermodynamics for a non-cyclic process, right. But if you look at the examples, whatever we have taken, that is valid, for the control mass system. Let me give you example of a control mass system and control volume system. Okay. For example, you might be knowing the hand pump. Any of you have used hand pump to get the water from the ground? Hand pump, you will be using a hand pump, right. And if you look at, like, suppose you have not used that pump for quite some time, and even if you press that pump or the actuators, right, you will not get any water. Did you observe any time? You may not have that experience, because I was having when I was a person like you. And nowadays people are using pump, which is, of course, they are calling it submerged pump, which is the down on the ground, and they take out the water very easily, right. Now, if you consider this system, I want to analyze, because some work is being done. Both are, as a matter of fact, is a what you call pump. Pump means to increase the what you call pressure, so that it will come up and like that. Now, which one will be the control mass system, which is the control volume system? I want to analyze this. This is a problem. One is hand pump, another is submerged pump, which is having a motor and impeller, like water is coming out. I do not know whether you have seen those things or not. Okay. Suppose I will take hand pump. How I am going to analyze? Because water is coming out, okay, and the other one, the submerged pump, water is also coming out. Okay. Should I give answer, or you will think about it? See, I want to analyze. Now, this is the situation, and I will have to apply the control mass or control volume, and then there will be some work done, and there is a change in velocity also. Fluid will be at the steel and the ground, and then it will be moving. So, there is a change in kinetic energy, right, and it is going at elevation. So, from the ground to the some height on your terrace, or in some tank which is at a higher elevation. So, there is a change in potential energy also, right. So, this is a beautiful problem for you to analyze using the first law of thermodynamics, right. Now, how to, unless I choose my control system, I cannot go about it. Okay. Now, see, let me just tell you, because you are not giving any answer. So, let me tell you that if we use the hand palm, then I can in a control mass system and what you call analyze it very easily as compared to the control volume system. Let me take another example, what you people will be using. I think in your hostel there will be geyser, right? Yes or no? Yes, you are having geyser, like you will get hot water in the summer season, in the winter season, right? And so that you will get a comfortable shower. Otherwise, it is very painful to have a cold water bath in the winter season. So, there some heat will be passed through and some water will be coming into the geyser and some water is taken out by you or by the user. So, I want to analyze that. Can I use a control mass system? Right? I can use as such, okay, but it will be little cumbersome to do that. And there are several system where the flow will be taking place, right. For example, fan, right, the flow does take place, some work being done in your wind turbine, in your gas turbine, right, and your compressors, car radiators, like do you know car radiators, right, what it will be in the front of the engine, right, what for it is, and pumps and nozzles and diffusers, there are several host of components or the gaskets what people have developed, and also several of them in which the properties of the fluid will be changing throughout the system as it moves. And like question arises how it will be, you will be applying first law of thermodynamics, analyzing it. For example, if you look at, there is a compressor, of course the diagram is not that good, but however you can see that this like it is having a what you call a shaft which consisting of several rotating blades, these are all blades which are rotated, and there will be stationary blades also, and that makes the fluid to compress the air or the liquid, whatever you will be using. And similarly turbine, in this case there is also consist of several kinds of blades, like as I told, rotary blades and stationary blades, and it will be what you call gas. If it is gas, it will be expanded and you will get some work done, like. So, if you look at this, will be rotating and you will get some shaft work. And similarly, if you think of some example of nozzle, some fluid will be going through this, and then what will happen, this velocity will be increasing, right. And in case of a diffuser, it will be other way around, there will be decrease in velocity. But question arises how we will apply the first law of thermodynamics and how you are going to analyze this, because there is some heat interaction and there is some also the work interaction, right, is going on. Now, because the mass is coming in case of any of this component, let us say for nozzle, mass is getting into the fluid, fluid is entering here and it is going out, and hence the control mass system is not convenient to analyze this kind of problems. This we call it as a flow problem, and such devices can be analyzed very easily using control volume approach, like one is control mass, other is control volume. We call it closed system, and this is one the control volume kind of things. Whenever we use a control volume, we call it as an open system. right. And then we will be now basically learning about how to apply the first law of thermodynamic flow system, because these are all flow is taking place, right. And let us recapitulate what we learned with the control volume. And if you look at the control volume is basically a what we call an arbitrary region in space, bounded of course by the control surface, through which mass will be passing through, right. And of course, if you look at, let us consider a system in which the mass is entering here, there is some shaft work is going on, and there is some heat interaction and mass is leaving out, and this we can consider that dashed line as basically a control surface, and this is the control volume, because the control volume is being marked, or what you call being bounded by the control surface, right. And this control volume, what you call one has to choose properly, right. And this control surface can be real, it can be imaginary, it can be fixed or it can be variable, right. For example, in this case, if you look at, is it this control surface is real or imaginary? In this example, what I have taken, is it what you call control surface is real one or imaginary? Real one means it will be having some kind of a what you call fixed boundary, which is maybe casing in case of your compressor or turbine, right. You can have a control surface that, because that is the boundary. And there is a imaginary. So, can you like whether this what you call these are the control surface, is it imaginary or real? Definitely it is a fixed one, it is not moving as the flow is entering, right. This is a fixed one, it is not movable, right. Am I right or wrong? Is it real or is it imaginary? So, let us look at, I mean like compressor, if you look at these boundaries which is corresponding to the casing of the what you call compressor, right. If you consider this as a compressor, then this is a real boundary, because it is corresponding to the actual boundary of the system. But whereas here the flow is entering, like there is a passage through which flow is entering. So, that boundary is imaginary boundary, and we can think of piston cylinder arrangement, and if the gas is entering here with high pressure, the piston can move, let us say piston is moving, and then what will be the, let us say it is having this boundary to start with, after that what will be boundary? Boundary will be this one. That means this boundary is moving. So, this is a moving boundary kind of things. And so, question arises how to choose a control volume. Is there any kind of a procedure or the rule for choosing a proper control volume? Right. So, it is actually you will have to use your judgment, and those choosing of the proper control volume you will be learning in fluid mechanics, because that is critical over more as compared to the thermodynamic problems, right. And there is no hard and fast rule for choosing a control volume. That depends upon the kind of problem, it depends upon the what kind of experience you are having. Rather I will put other way around, it will be depending on how you think, right. because sometimes it will be convenient for you, but for it may not be convenient for others. But however, one has to use choose the control volume and a control surface accordingly diligently, right, such that it will be easier to handle the problem. So, we should keep in mind that for a open system or a control volume system, not only the heat or the work, but also the mass can cross the control surface, and there will be interactions, like in this case the fluid will be entering and leaving, and sometimes entering not leaving, sometimes leaving not entering, all those things can happen, and it may be accumulated also. So, that you should keep in mind. So, let us look at what are the processes we can consider, right. Processes can be what you call steady. It can be transient process as well, right. Steady process means no change in flow properties with time. For example, like if I take a system here, let us say this fluid is entering and fluid is going out, and let us say this is something what to call 300 degrees Celsius, and it may be 400 degrees Celsius. Of course, there will be heater here, like there will be some heat input, and this is at time, let us say 9 a.m. and I will consider the same thing, like same system I am considering, same. So, if it will remain here at 300 degrees Celsius, 400, same thing at let us say 9 p.m. in the night, morning till night, let us say we are considering that period of time, then we call it as a steady. But if it is changing, of course, it can change within an hour, it can change within this thing. So, then we consider this as a unsteady process or transient process, in which the flow properties will be changing with time, right. But whether there is another process what we call as a uniform flow, that means no change of flow properties over a special location, right. For example, I will take a flow over a flat plate, there is a plate over here and flow is coming, let us say it is a uniform velocity 10 meter per second. As it moves, because of boundary layer, see this is the boundary. So, the velocity will be here 0. So, therefore, it changes, and because of viscosity, and the flow is not uniform here. Earlier we have given input as a uniform velocity profile, but here the velocity has changed, and this flow in this case it will be uniform properties, and here it is changing. So, also the other things will be changing. Now, that we call it as a uniform flow. Let me just tell you that in case of thermodynamics, we will be considering most of the times, rather all the times, right, or most of the times uniform flow, right. In fluid mechanics, when you will analyze, you will be using non-uniform flow kind of things, right. That you should keep in mind. And you might be wondering, like whether the unsteady process will be occurring all the time or the steady process, how to choose, and then whether the steady flow process will be really occurring, right, or all the process will be unsteady. So, as you go along, we will see that that there are some processes we can happily assume to be steady, provided steady over the period for which we are analyzing it, that is important. So, as I told that the mass of the system remains constant during a process in case of a closed system, there is nothing to worry about it, right. And whereas the open system mass can cross the boundary. So, we need to keep track of how much mass is crossing the boundary, inlet boundary, outlet boundary, right. There might be several inlets and there might be several outlets. We need to have a bookkeeping of the mass entering and leaving kind of things. Let me just take you a control mass system, like you are having, let us say, one jug kind of things, right, where you are mixing water and milk. Let us say 3 kg of milk is mixed with 1 kg of water, that became 4 kg of water milk, that what our milkmen they do very often. What it indicates? Indicates that mass is conserved, right. So, that means mass like energy is conserved, okay, property, because we know that energy can neither be created nor be destroyed. Of course, it can be converted from one form to other, right, that we have seen for an isolated system. And if you look at, can I say that also similar way mass can neither be created nor be destroyed? Can I say that way? Mass can neither be created nor be destroyed, right. It may be converted from one form to other. For example, water, water is converted into liquid, water is converted into vapor, or also the ice, Now, let us take an example, right. The 1 mole of methane is reacting with 2 moles of oxygen and going to the product 1 mole of carbon dioxide and 2 mole of water. And of course, some amount of heat will be released, right. So, if you do, I mean, this is a balance equation or not, am I right? If you look at this, basically balance, because if you look at carbon, this 1 carbon, this side left hand side 1 carbon, right hand side 1, and this is 4H4, this is also 2H, 4 basically 4H, and similarly oxygen, if you look at 4O and this side 2O and 2O plus 4O. So, it is balanced. And if it is balanced, what it says? Is it like if you look at it is balanced by mole wise, like 1 mole of methane it is reacting with 2 mole of oxygen and 1 mole of carbon dioxide reacting 2 moles of water. So, if you look at mole wise, left hand right hand side is same, am I right? 3 and this 3, right, total. But what about mass? Mass is also 16 grams, right, of methane is reacting with 64 grams of oxygen and giving rise to the product of 44 gram of carbon dioxide and 36 grams of water, right. If you look at left hand side is basically coming to the 80 grams, right hand side 80 grams. So, we can say mass is conserved in a chemical reaction. In a chemical reaction, some heat will be released and then in this case heat being released, right. So, it is happening, it is basically. So, can I say that mass is conserved, right? Yes or no? But we have taken this example, we are saying that mass is conserved, right? Yes or no? Mass is conserved, no, right? And in case of your fluid mechanics and other thing, we will be using the conservation of mass, right? And heat transfer, other problems also. So, but is it really true, right? Or it is true for some situation? How many of you agree with this? Mass is conserved? All of you, huh? Yes, right? How many of you people agree that mass is not conserved, mass is changing, right? So, only 2, okay. So, let us look at actually what this Einstein relativity theory says, E is equal to mc square, right. The E is the energy, c is the speed of light, mass is the m is the mass. So, if you I will take this example and try to compute how much change in the mass because of heat release, right. So, I mean that we can see that, but what this relation says that energy can be converted into mass and vice versa. So, therefore, there will be some change. If it is changing, energy is converted to mass, that mass will be consumed, right, and converted into energy. So, let us look at considering that example of methane being burnt with a reacted with oxidizer, converted into carbon dioxide and water, and that gives rise to something 1 kg of methane. When it burned, it gives 50,000 kilojoule of energy, right. And we will substitute these values over this here, right. And we will also know the speed of sound, and this is speed of light, right. And if you do that, you will get this mass is very, very small quantities, like means 0.556 into 10 power to minus 9 kg, right. It is a very, very small mass change due to this heat release. So, which is cannot be really measured with the best instrument available at this moment. Hence, the mass conservation is quite valid for our thermodynamic analysis, even for fluid mechanics heat transfer, unless some nuclear reactions are being taken where the large amount of heat being liberated or large amount of energy being liberated, where there will be some change in the mass. There you cannot afford to consider the mass is conserved, right. I mean there, but rest of the things you can happily assume the mass is conserved, right. So, let us consider how we will handle this mass conservation principle for controlled volume system, because we are considering for thermodynamic system mass is conserved. So, we will take this example in which if you look at let us say there is a inlet here in this chamber and there is outlet, and 5 kg of mass is entering I mean during 1 second, and then it is leaving with 3 kg of mass, and this is something accumulated 2 kg kind of mass, that we can write down mathematically as, let us say dmi is the mass entered into control volume at during time dt, and dme is the mass leaving the control volume during time dt, and mt is the mass inside the control volume at time is equal to 0. That is, we can in this example we can consider as a 0 kg in this example, and the mass inside the control volume at time t plus dt is 2 kg, right. And if you look at mass entering the control volume during time is basically, if you look at this is 5 kg and this is 3 kg, right. Now, we will what to call look at this how it is happening and derive an expression for that. And if I will just do a balance between the inlet and the exit, if you look at mass is at time t plus dt minus the mass at time is equal to dmi minus dme. The mass is going to the inlet, this is your inlet, and this is your exit. So, if I will divide this by dt and this is by dt, right, time, and this time is very, very small and is tending to 0, what you will write down? And if you will write down that, it will be like this, and then we can write down that when dt tending to 0 is nothing but dm by dt is equal to m dot I, this dot is basically per unit time, right, minus the mass leaving at the exit, mass flow rate leaving at the exit, right. And this is what you call the mass conservation equation. What it indicates? If you look at the left hand side, this term is basically mass being accumulated in this control volume, and this mass is entering into the control volume, that is m dot I, and mass is leaving from the control volume, right. So, and this will be basically taking care of mass balance, we call it mass balance, how much is the mass being accumulated in the control volume and mass being leaving in the control volume, and rate of the mass entering into the control volume. In this example, I am again repeating that the accumulation will be 2 kg per second, and the mass which is entering into this control volume here is basically 5 kg per second, and mass leaving is 3 kg per second. So, this basically you are taking a mass balance. It is like like in your bank account, your father will be sending some money and you will be spending, and whatever the difference is accumulated, and sometimes it will be negative as such, right. So, of course, in this situation it will be, if it is then kind of things. So, and now this equation is meant for a on a single inlet and exit, right. But there might be a situation where there will be several inlet and several exit. For example, I do not know whether in your hostel it is like that, from the one geyser you can have several connections, right. One is inlet pipe and several things are going. For example, in the houses we do, let us say we are having 2 bathrooms, so we will put a one geyser and give a connection to the other bathroom, right, or washroom, whatever you call. Nowadays, people are calling bathroom as washroom, okay, the new terminology for me also. So, it is fine, and then there will be multiple inlet will be there and multiple exit will be there, but how to handle that? For example, in this case, there is a one inlet what I gave, like let us say mass flow rate m dot 1 at the station 1, if I consider this as a 1 station, and this is your station 2 and this is your 3 kind of things. So, how to handle this then mass balance on this? And what you can do, you can just rewrite the equation 2 as dm by dt is equal to mass flow rate accumulated in the control volume is equal to summation of m dot I minus summation of m dot E, right. So, in this case, in this example, this in the inlet, if you look at inlet there is only one, right, but there are 2 exit or the outlets, right. So, therefore, 2 mass has to be considered, it may be n number of things, right. If you look at like this can be n is equal to 1 to whatever n may be, right. I can say number of exit will be n, n is the number, it can be n number, it can be 10, it can be 5, it can be 12, it can be 1, it can be 2, anything, okay. So, by this we will do a basically mass balance, what you call keeping up the mass flow rate into the control volume and leaving out of the control volume, and also the how much being accumulated in the control volume. So, now we will have to learn how to apply the first law of thermodynamics for analyzing an open system, right. How we will do that? Because whatever we have done, that where mass is not coming in and going out to the control, what you call surface in a control mass system, right. Now, can I apply that equation? That is, what is that? dE is equal to dQ minus dW, that is the first law of thermodynamics for control mass system, right. And there, if you look at, if you just think about, there is no rate term. Can I really rate in the sense mass flow rate per unit time? It is not there, right. But I can apply that equation for the rate term as well. Am I right? Yes or no? I can divide the time per all the denominator, and then becomes, that is all I can say. But how we will apply? What we will do now, we will be considering basically a control volume system consists of several control mass system, right. And then we will apply this control mass system equation and then derive a relationship which will be hold good for the open system or a control volume system. How it is? For example, if you consider the video, right, then video will be consist of several still photographs. Am I right? You might have taken several videos and converted into still photograph. Am I right? You have done or not? In the similar way, what we will be doing, that we will be transferring the flow process into a series of imaginary non-flow processes in succession, like the way we convert the video into several still photographs, right. For example, if I am moving this hand like this, the hand can go one state to another, but it can go several places. So, I can consider one state and then go another and another and analyze. Similar way we are going to do that. Is that clear? This is a very important concept. You must try to visualize, then only you can, otherwise no, right. Are you people getting what I am trying to say? That means this flow process will be converted into series of non-flow processes in succession. Let us do that. What we will be considering, that this process, like let us say this is the your control system, control mass system, in which you are having, and this is of course initial state at time, it is having a shaft work, it is having a heat input, and then you assume that this fluid A is about to enter into this system at time is equal to t. And let us consider at the final state at time is equal to t plus dt, then if you look at, this is my now control, what you call control mass system here. That means this portion will be my system, right. In the time t, what will my system? My system is this one I am considering, this, right. That means coming from here and going, this is my control system. And at time t plus dt, this is my including this fluid which is about to leave from this volume, this what you call. Is that clear? That means the fluid is coming in and going out, coming in and going out, that we are considering. So, with this mean, that means at time t, this is basically we can say it is a control mass system here at time t, and at time t plus dt, again this is the control mass system, but its boundary of the system is changed. The boundary becomes like this, right, and here it is considered the inlet fluid which is about to enter. And in case of time plus dt, it is also contains whole boundary, but the what you call the mass which is about to leave this chamber. Is that, are you people getting or not? That is very important point, and you should try to visualize and keep in mind this is the thing what we are considering. Now, during this time dt, mass in the region A enters the control volume and certain mass leaves into the region B, that we are considering it in 2 instant of time, that is. So, and some of the work is required for the mass to put into the control volume, and that of course we call it as a flow work, and also some work is required that by which the fluid will be moving, what to call moving out from the control volume, right. Are you getting? For example, that means I need to push this fluid to enter into here, right, that is some work, and that we call it as a flow work. And similarly, this fluid has to go out, and then we will have to push some out, so that it will be what you call some flow work is required to be given. So, for you can think of, imagine that this is an imaginary piston, right, this is a piston kind of thing which is imaginary. It is not there, I am just assuming that there is something pushing, that makes piston. Similarly, here it is having a suction, this is also a imaginary piston which is moving out, so that fluid will go out. It is not there in actual system, okay, but we are just thinking. And now what I am trying to say that the fluid which will be before entering, it will be like that with a pressure P and a specific volume V, and is entering, and after entering it goes there, that is the flow work. If you think that way, that piston is here, and when the force is applied, then it moves with a distance L. So, then what will be work done on this? That means, I am taking this imaginary piston, which is this fluid which will be entering into that by the imaginary piston. So, how much work has to be done then? What will be work done? We know that, that will be P dV, right, and that is nothing but what I call flow work, P into A into L, right. This portion is your change in volume, right, and that of course I can say this change in volume V, PV kilojoule, right, per unit mass. What it would be? This will be P into specific volume, that is kilojoule per kg. This is your pressure, and this is fluid pressure, and V is your specific volume, right. So, that means we can evaluate how much work is done, and like of course, if how much work is done during the time t, and so let us consider that the work done will be at the inlet is basically P I V I into mass flow rate, what is entering. So, this whatever entering is m dot I, right, into dt, and during time t dt. So, that will be work done at the inlet, and this is your inlet, and this is your exit, right. And negative sign, why negative sign is coming? Because if you look at the surrounding is doing the work on that. So, therefore, it is not by the system, it is on the system. So, it is negative. In the similar way, we can find out work done by the flow at the exit during time dt will be W e P e V e m dot e into dt, right. In the similar way, only the sign became positive because the work done by the system, whatever it is, by the fluid rather, fluid in this case is a system. So, the total energy of the fluid E total at time t will be what? It will be basically energy of the fluid at time t plus some amount of fluid, energy, the fluid with certain energy of E I is entering during time t at the inlet, right. Are you getting? So, that means this, because of this mass flow rate is entering, it will be having certain amount of energy, right, and it is occurring during time dt. Of course, dt we are considering to be very small, that we will be doing. So, what is that E? E is consisting of what? E stands for what? Total energy. Total energy means it will be having internal energy, kinetic energy and potential energy, right. So, that together, so that is basically u plus m v square by 2 plus m g z, z is the elevation, right. And of course, if we just divide this with the mass, that became total specific energy at time t. Okay. So, similarly, at time t plus dt would be E is equal to E, that energy in the control volume, whatever it will be there at t plus dt, plus the whatever the energy about to leave from the control, that is m dot t E e into dt, right. We have done for the inlet, we are doing for the exit, considering that is all, nothing more. So, now what we will do? So, how much heat is transferred to the control volume during time t dt? That is basically q dot into dt, right, is equal to energy transfer as heat into the system. There is also work interaction, right. So, how much work is being done during time dt? That is w dot into dt. Basically, this is kilojoule per second kind of thing, you can think of unit, into dt. This is a kilojoule and work done by the system. And according to the first law of thermodynamics, that we know d is equal to dq minus dw and dq minus dw plus dw, and this is the flow work, right, and this is what you call any shaft work one can think of, like so. Therefore, we can say that E by t plus dt, right, and this is the energy, right, this is this term at t minus at the what you call at the t is equal to 0, this amount of energy E t plus m dot I E I dt, and this is your heat interaction minus the work interaction, and this is your flow work, right. We have already seen m dot E P E V E minus m dot I P I V I into dt, and during that time dt what is happening, right. You are getting that each term is for basically what you call is for control, if you like, at t dt is one control mass system and t is another control mass system, you are combining it and then looking at it, right. And what we will do, we will divide this term by dt. So, if you look at, I will divide this term dt and I will divide by dt here and also dt here, and when dt is tending towards 0, so I will get an expression dE by dt is equal to m dot E, in the bracket if you look at UE, I am just expanding that E, right, and VE square divided by 2 plus GZD, and this flow work I have taken over here, if you look at these kind of things, I have already taken here flow work, and this E I am expanding, this is the expanding version till this, right, till this is the E and this is your flow work, and this is at the inlet is equal to Q dot W, and where HE is equal to U plus PE VE, that is enthalpy, right. And similarly, I can write down HI is equal to UI PI VI, and then above equation becomes the dE by dt is plus m dot E HE plus the kinetic energy term V square divided 2 plus GJD, and this is at the exit minus the inlet total energy, right, m dot E into HI plus VI square divided by 2 plus Gj di is equal to Q dot minus the work done. So, this is the energy equation for a flow process or a open system. So, which is quite complex as compared to the first law of thermodynamics for a control mass system. So, we will stop over here and we will discuss in the next lecture how to apply and what are the things and other things.